Hey everyone, good afternoon. Today we're starting a new set of topics. We just spent the last 4 weeks talking about kind of the most modern and applicable deep neural networks out there, and the goal was to give you a solid understanding of how they work and enough to where you can go read papers about really cool CNNs and understand what's going on. So obviously it's impossible to cover everything SOA, state of the art, but we believe that the deep learning the deep learning book set of topics is nice. And by that I mean the part that we're starting today is going to be centered on research topics. So a lot of stuff that's been going on, both in the past that's been revitalized and stuff that's being worked on now. Primarily generative modeling stuff. So a lot of people believe that some of the most interesting developments in deep learning will come out of generative modeling. So all these deep network things are really cool. Like we can do really cool things with NLP, natural language processing, and computer vision, but we're not really gaining anything as far as progressing into solving the more general AI problem. So if we can get a better understanding of how things are generated, how people think, how nature thinks, we can start to understand better how machines think. And so we're going to be really concerned with probabilistic models. So for those of you 189, you spent the last 4 weeks learning about probabilistic models. And they come back, and they actually are important. So high isn't wasting your time. Probabilistic models are a super important way to look at data and its generation process, and can also give us a better understanding of underlying processes in order to make better decisions. That all said, my slides today are not too good. So by that I mean there's too much material in them. They're not optimized to give a nice presentation on LFMs in an hour. I put everything that I could in there, so I'm going to skip over a lot of things and focus on other things. Don't worry if you don't follow everything. My goal here today is to give you a solid understanding of what a latent variable is, how to estimate it, and a basic understanding of a factor model. I'm going to give you a lot of different kinds of factor models, a lot of variations, a lot of improvements, a lot of pros and cons, and don't worry if you don't catch everything. The goal is to give you a gist of what these things are and to teach you how to think in this probabilistic setting. With that said, here's this ambitious list of topics that I was hoping to talk about. So first I want to tell you a little bit of background where we are while we're even talking about linear factor models. And then I'll introduce a couple of different ones. So I'll introduce probabilistic PCA, which is just it's very similar to standard PCA. The setup's a little different, and we'll see how. I'll talk to you about independent component analysis, which I think is really cool. Slow feature analysis is also a really cool type of linear factor model. And then sparse coding, which was invented by Bruno Olshausen. How many of you know Bruno in the Redwood lab? Yeah, so Bruno invented sparse coding, and it's a pretty cool unsupervised learning technique. And then just for fun, the last section of the book is on manifold learning, so can't let you leave this deep learning class without learning how to learn manifolds. That wouldn't be kosher. So yeah, I do have some warnings. So actually, this is not the warning slide. This is just a where we are slide. So yeah, we all know how to train deep networks and optimize them and figure out how to tune dropout and how to do hyperparameter searching, and we know how to change kernel sizes and how to select the depth of our network and how to train models and benchmark them and compare different kinds of networks. But as I said before, many of the frontiers in deep learning research involve probabilistic models where we're modeling the generation of the data. And the goal of this is because we want to use probabilistic inference to predict any variables in its environment given any of the other variables. So given a collection of variables, can I predict the outcome of another variable? but in an unsupervised fashion. So here's a very basic setup for a probabilistic model. Many of them have latent variables h. And latent variables are just another way to represent the data. And latent variables are really cool. We'll see why in a sec, but basically the idea is that distributed representations based on latent variables can obtain all the advantages of learning, which we have seen with deep networks. So by representing my data in terms of its latent variables, apparently I have all the advantages that I get with deep networks, which is really high capacity models. So just a little primer on latent variables. So as opposed to observed variables, so we usually talk about an x and a y. We observe x and we want to predict y, or we observe x and y, and then we want to use new x's to predict new y's. Latent variables are different. We don't observe latent variables. They're rather inferred from our observed variables. And latent variable models are ubiquitous all over science. So in psychology, economics, engineering, medicine, physics, MLAI, bioinfo, NLP, management, and everywhere else, latent variables come up. So here's an example. In economics, we often want to measure happiness. We want to have some data of the happiness of our constituents or of our people, of a certain state or a group of people, etc. But I don't know about you, but I don't know of a direct way to measure happiness. I can ask you how happy you are 1 to 10, but that doesn't seem like the best way to actually get how happy you are. There's probably a lot of confounding factors and a lot of noise if I were to collect happiness data that way. So a lot of things that modern economists do to get a sense of happiness is to measure things that may correlate with happiness, that may contribute to happiness, and try and infer happiness from those measured things. So things that we can measure include wealth, employment, environment, physical health, years of education, leisure time, etc. And the hope is that by measuring these variables, we can infer something about the happiness of those people. So in this case, the latent variable is happiness. We don't observe it, but we can infer it. Our latent variables are represented by the observed variables distributedly, in a distributed fashion, sorry. So, latent variables. You can kind of begin to imagine why we would care about latent variables, right? We can't collect data about everything, but we want to know about everything. So it's going to be useful to use things that we do know to find things that we don't know, in essence. Cool. So any questions so far? So this slide is my disclaimer slide. So yeah, so there's lots of probabilistic models. Linear factor models are not the only one. A probabilistic model is any model of the form P of x. We're modeling the distribution of x. It's basically a fancy word for kernel density estimation. Not entirely, but it's an umbrella. It's more or less pretty similar. So linear factor models are just one kind, and they're the simplest kind, and that's why I'm starting today talking about them, because many of the future models, the cooler models that you might have heard of, like Boltzmann machines and GANs and all these other ones, are much more complicated factor models. And so here's my warning. You probably won't implement any LFMs to solve state-of-the-art problems, but as I hope to distill on you, they're a nice building block for more complicated, deep probabilistic models, which we'll care a lot about in a few weeks. And if you don't understand this stuff, that stuff will be a lot harder to understand. So yeah, many of the stuff that we'll talk about today are a necessary framework to build more advanced deep models. So keep coming to class. Okay, I've spent enough time beating around the bush. Let me tell you what a linear factor model is. So a linear factor model is defined by the use of a stochastic linear decoder that generates x by adding noise to linear transformation of h. So we assume that our data x is generated by some linear combination of some latent variables h, which we don't observe. And linear factor models allow us to discover explanatory factors that have a simple joint distribution by us artificially forcing them to have a simple distribution. And the simplicity of the linear decoder motivated, like I said, these slides are bad, there's probably lots of typos, so I think there's one right here. Simplicity of the linear decoder motivated these as some of the first latent variable models. Actually, that's not a typo. The linear decoder is linear, it's simple, and so might as well start simple with the first latent variable model. Cool. So here's what I said before, but with math. So here's how LFMs describe the data generation process. So we assume some explanatory factors h from a distribution. I have no idea what that distribution is, but I make an assumption that's a factorial distribution, that the joint distribution can be rewritten as the product of the marginals. And then I sample the real-world observable variables given the factors x equals wh plus b. So b is bias, noise, we have some noise, and w is this weight matrix that gives us the combinations of h to yield x. So now we're talking about a completely different framework here. We're talking about how the data is generated. Before the last few weeks, we've talked about we have some data. Can I learn to create a mapping from image to label or from block of text to sentiment? This is completely different. This is concerned with how was this image generated? How is this block of text generated? And that's what the latent variables describe, hopefully. Not always, but that's what their goal is to do. That's what they're intended to do. So yeah, here's a very simple LFM. So I have some latent variables, which I don't observe, and then my model assumes that the data that I observe, x, is some linear combination of those h's. Cool. So as I said before, there's lots of types. So this slide is kind of the general LFM family, but there's not too much detail here. But the general LFM family follows the scheme. We observe x, but we obtain it from a linear combination of independent latent factors h plus some noise. If there's anything I want you guys to have understood so far, is that latent factor models assume that our data generated is a combination of latent factors which we don't observe. And you can imagine maybe one of our goals is to recover those latent factors. That's where we're heading. So all these kinds of, yeah.
But it can also be latent factors plus like non-latent factors, right?
Sure, yeah.
Okay.
Yeah.
Yeah.
Yeah. So these are just the four that we'll talk about today. There's a lot more. And there's lots of differences between the models, but I guess the main difference is summarized here is that different types of LFMs make different choices about the form of the noise in the prior. So remember those h's that we were so concerned about? We assume that they come from some distributions. There's some underlying distribution that describes the distribution of the h's. And that's some prior that we don't know, but we use our best guess to estimate. And choosing the prior has a lot of effect on the model outputs or the model performance. And so a lot of these different LFMs are just clever choices of priors. So I think we'll start with probabilistic PCA. Or actually a little first stint on factor analysis. So this isn't necessarily a model, just as much as like a setup. I guess that's not fair to say. Factor analysis is kind of like it's like the most general factor analysis, and then we'll get more and more specific. But yeah, it's been around for a while, as you see, more than 20 or 30 years. And here the assumption on the prior is that it's standard normal. So we assume that h comes from some unit Gaussian distribution. And then we assume that xi, the observed xi, are conditionally independent given h. That is, the noise is drawn from a diagonal covariance Gaussian distribution, and since this is just verbose. Conditionally independent implies that the covariance matrix is diagonal. And then the goal here is that the latent variables capture dependencies between the x's. And then if you want to find the distribution of x, you can do some math and show that x is normal with this distribution, assuming that x equals wh plus b. So if h is this distribution and x equals wh plus b, then x has multivariable normal with mean b and covariance matrix w transpose plus psi. confusing, I know. Just the idea is the important part. Probabilistic PCA. Let me keep an eye on time. So here we're slightly modifying the general factor analysis model. And basically this is casting PCA in a probabilistic setting. There's really not too much exciting stuff to say here.
Here's what I found on the web for a new prop.
Sorry. Trying to keep track of time. Yeah, there's nothing too exciting here to say. Let's keep going, and I'll pause on the important points. What probabilistic PCA can do is that it can capitalize upon the fact that most variations in data can be captured by latent variables, H, up until some small residual reconstruction error. So your question about our observed data being a combination of latent variables and non-latent variables, I wouldn't know what that would mean, having non-latent variables. So what that's saying is that I observe my x, and my x that I observe is a combination of latent variables plus other x's. Yeah. Maybe. Let me think about that. But assuming that there's no latent variables, we can represent our data by only the latent variables using the linear combination via W, the matrix W. And apparently it's good enough. Using only latent variables as a representation for our data allows us to reconstruct the original data up to some small reconstruction error. And these guys show that it's the same thing as PCA when sigma goes to 0, where sigma is some noise. So basically we're adding noise and then doing PCA. Let's see. I don't want to talk to you about this. This is some like subspace intuition. Yeah, sorry. You can read that on your own, slide 15. But I do want to talk about the motivation. So PCA is a linear dimensionality reduction technique where we assume linearity, linearity between the bases of the linear combination of the measurement basis. And we also assume that large variances mean important structure, right? That's how we order our principal components in terms of the magnitudes of the eigenvalues. And then we also have to assume that principal components are orthogonal. Those are a lot of assumptions, right? So linearity is not always justifiable. Doing PCA in its vanilla form in high-dimensional space may not be feasible. You have to calculate a covariance matrix, which is order nm squared, like something almost cubed. And then it turns out that decorrelation is not always the best approach. So decorrelation means that we're decorrelating the representations. We're discouraging latent variables from being related to one another. We want them to be to explain different things. Yeah, sorry. This is just. I apologize, but I apologize again. This is not a nice slide to look at. Just know that probabilistic PCA is an alternative to PCA, and it's a common latent factor model. I don't think there's anything else important to say about it. I've never used it. I've never seen it used, but it's the first thing that Goodfellow talks about in the book. But this is just some information about it. I do want to talk about more. What I do want to talk about more is independent component analysis. I think there's a lot more interesting things to say here. So it's actually one of the oldest representation learning algorithms. And in ICA, we're modeling linear factors by trying to separate an observed signal from an unobserved signal that are scaled and added together. And you'll see what that means in a second. And the signals that we're trying to separate are intended to be independent. We're trying to break down our original signal into a set of independent components. That's abstract. Let's see why. Okay, this is just a variance of that. So we generate the independent signals from this prior. We deterministically generate x via this transformation. And then the nonlinear change of variables allows us to determine p of x, which is what we want. And then you can learn the model via maximum likelihood. Probably that means learning W, I guess. So here's what that means intuitively. So you see our the top two are plots showing a mixed signal and its true source. So there's really three signals here, and we observe like a noisy version of them, whereas they really came from this true source. And the goal is to reobtain the original signals from the noisy mixed signal. And so if you try to do that with ICA and PCA, you see two different things. ICA gives you something that looks like this. If you try to run PCA, you get something like this. And so I don't think it'd be a far-fetched argument to say that ICA does a good job at decomposing the independent signals. But we'll keep talking about it. I know it's still a little hard to get your head wrapped around. So remember that we said that LFMs differ based on the choice of the prior. Here we choose the prior such that each sample generated by choosing P of H to be independent. That doesn't make sense. It's a distribution. Independent from what? Yeah, so we're forcing this assumption on this prior, which allows us to hopefully recover as close to as possibly independent signals. And they're low-level signals that have been mixed. Again, each point that we observe is a mix of the original signals, HI. Oh, here's an example that might help illustrate this better. So we have, and this is actually where something like ICA has been used. So we have n different people speaking simultaneously in n different microphones in different location. And so what ICA can do is it can detect the change in volume between each speaker as heard by each microphone and separate the signals so that each HI contains only one person speaking clearly. So I have all these noisy signals of people talking on the microphone, and I want to extract each person's sound at a time. And so that's something that ICA can do. Does that example maybe help illustrate it better? You have n different microphones, n different voices, and I want to get back each individual person's voice or sound. Yeah.
So if you go back to that the figure with the observations, so this figure is basically showing that like the PCA only identified one major one, and the other two were kind of irrelevant.
Yeah.
Well, the ICA, although it had the wrong shape, except for the blue one, I think, it did identify three different sources. Is that what this is trying to show?
Yeah, it identified three different independent factors, whereas PCA failed to do that.
Okay, even if they weren't necessarily accurate, the important thing is to identify them.
Yeah.
Okay.
And I don't...
Wait, is it important that like the colors are swapped? It doesn't seem like it should matter. It was able to identify a signal shaped like that.
Between the second and third one?
Yeah, like you're just saying that because it went from red to blue.
No.
But there's
It's saying that the
no
ramp
like-
flipped and also.
I mean, also like one of them is split.
Yeah.
But it looks like blue went to yellow, red went to blue, and then.
Oh, I
yellow went
just
to
saw
red,
it
and
wrong.
flipped
You're
it.
right.
Yeah.
Yeah, I just didn't see that.
Yeah.
Yeah.
Cool. Yeah, thanks. So here's some applications of ICA. So other than the microphone example, you can use it to separate spikings of neurons. So if I have data that shows me different neuron spikes, I want to separate the spikes to depending on what they do. That's very abstract. But BinU does this kind of stuff. So yeah, you can imagine how it would be used in neural spike sorting. It can be used in these other contexts as well. So for communications, for removing artifacts, like getting rid of the noise from an image, predicting prices, and imaging stuff. So some more stuff. Is there anything important here? Again, the aim is to make the latent factors independent. And if you restrict W to be orthogonal, it can reduce computational cost. Some variants add noise. But all variants of ICA require the prior to be non-Gaussian. Having a Gaussian prior causes a problem in terms of ICA. Cool. So another thing on this slide that I would say is that not every type of ICA that you'll see will be a generative model. There are variants that are not necessarily generative. It can be generalized. So feel free to read slide 24 if you want to read about a cool generalization. That's kind of like a modern ICA from 2014. So I'm going to skip it though, for the sake of time. Slide 24 though. Okay, so before we required independence between the subgroups, that's kind of not realistic, right? Independence is a very strong assumption for most things. And so a good generalization to think about is, can we relax this independence assumption? And you can, and so other cool things happen. So let's see. Yeah, so you can discourage dependence rather than prohibiting it, and that may help with generalization. Apply to natural images. So So how many of you have heard of Gabor filters? So Gabor filters are a filter that you apply on an image and it gives you like edges and stuff, or not edges, but like outlines of certain ridges on your image. So it was shown that if you train a CNN, early layers in the CNN act as Gabor filters. So it's pretty cool. Okay, so as I said before, I don't expect you to follow along completely. There's way too much stuff here, but I really hope you got the gist and the main ideas of what else I've been to convey so far. With that, I'll stop for any questions about anything. Yeah.
Yeah, how do you find that ICA compares to PCA? Because it seems like they can be used for pretty similar applications. Like you mentioned facial recognition and like detecting artifacts and like EKG data for both. So how do they compare in applications where you can apply both?
I've seen PCA a lot more used than ICA. I've only used ICA a handful of times. It's hard for me to comment on its effectiveness in a variety of applications.
Yeah, like PCA seems to be used more widely, but in the one example, like quantitative example you showed, it seemed like ICA did a better job.
Yeah.
Then we use PCA to do that.
I don't know of any rule of thumbs of when to use one over the other. I think that's a good thing to know. Maybe I can try and look into that and get back to you about when ICA is definitely preferred over PCA. Okay. But I hope to at least give you the understanding that both of them exist, and so that way, when you're attacking a problem, you now have more tools in your tool belt, and you can try them both. So this next linear factor model is pretty cool, but doesn't really work too well. But the reason I'm presenting it is because the underlying idea is super cool, and I think that, maybe I don't think, but I'd like to believe that this idea is going to be pushing the boundary of AI. It's a really cool idea called the slowness principle, and we'll see what that is. So again, just another type of LFM. So far we've seen factor analysis models, probabilistic PCA, and what did we just talk about? ICA, independent component analysis. Now we'll talk about slow feature analysis. Cool. So what it does is it uses information from time signals to learn invariant features. Let that sink in for a sec. But this whole thing is motivated by the slowness principle. And the slowness principle says that important characteristics of scenes change slowly compared to individual measurements that make up the description of a scene. So the example kind of is a toy example of that particular thing, where suppose we have a zebra that moves from left to right across an image, so we have like a video, and individual pixels change rapidly as the zebra stripes pass over. So like if you look at the grid of pixels in our image, each one changes very quickly. but the feature that indicates whether or not a zebra is in the image changes slowly. So individual pixels change very fast, but the high-level feature of is there a zebra in this image changes much more slowly. And so the thing I think is really cool here is we want to regularize our model to learn features that change slowly over time. Doesn't that sound pretty cool? A lot cooler than it actually is, but I think it sounds pretty cool. So we're regularizing time, essentially. Regularizing on time. So here's how you can add the slowness principle to a model. It's just another regularization term. And you can add it to any differentiable model. You can add this to neural networks if you want. I've never done it. Don't think anyone ever has, but go ahead, please. I don't think it's pretty hard to add your own loss function in TensorFlow. So you can try this out for fun and see if this does anything, especially with video data. There might be some interesting experiments you can do here. I think that'd be a really cool project. Just try to implement the slowness principle for deep networks and try to see how the learning process changes when you penalize time. That'd be a cool project. I would do it if I'm too busy. So lambda hyperparameter, strength of the slowness regularization, t is the time index, f is the feature extractor, so f is our model, and L is a loss function. So here's a visualization of the slowness principle. So at the top we have a video of 5 frames of I think it's a parrot or a bird, and we're measuring the primary sensory signal, and then we also get the slow features. We can see how the high-level representations change over time. So you see that as the bird exits the frame, oh, it's a monkey, sorry, it's not a bird. It says right here it's a monkey. So as the monkey leaves the frame, our measure of high-level representation goes down. Whereas the primary sensory signal doesn't change whether or not the monkey is in the image or not. The primary sensory signal just measures some kind of pixel measure. I'm not sure exactly what it is here. So the way this algorithm works is it applies a linear feature extractor, and what's cool is it can be solved in closed form. It's not exactly a generative model because it actually defines a mapping between input and output space, a linear map in this case. And for SFA, we don't impose the prior over the feature space. And so we don't have some imposed distribution on the input space. We don't have a PH or a PX. Yeah.
What if we had a nonlinear feature extractor?
I think that'd be okay. That would just be taken into account into your loss function. So sorry, let me clarify that. So SFA in particular works by having a linear feature extractor, but you can apply the slowness principle to your model by adding this loss function.
Oh, I see. So SFA, because it's linear,
yeah,
it's a closed form solution.
Yeah, SFA is a linear factor model. It's going to have a linear feature extractor and decoder. Okay. Here's what the algorithm looks like. So we define this function f to be a linear transformation, and we solve the optimization problem. We're looking for theta that minimizes this. Now stare at that and see if you can think about why we want to minimize something like that, especially with those constraints. We're constraining the mean to be 0 and the variance to be 1. Well, the reasons for the constraints are here, but think about why we want to solve that optimization problem. And yeah.
We want our algorithm to identify similar things as time progresses. So we want, if over a second, we don't want it to change too much.
Yeah, exactly. We want to measure things that don't change too much over time. We want to extract those. So we're penalizing we're penalizing big changes over time. Or we don't want big changes over time. And the mean zero constraint ensures a unique solution, and the unit variance constraint ensures the trivial solution in which all the features collapse to 0. So like as in PCA, when we find our principal components, they're ordered in terms of a magnitude of importance. And just as in that, the slowness components are also ordered, with the slowest one being first. And then so, like in PCA, when we find one direction which best captures the variance of our data, we can find another direction that's orthogonal to that in the same fashion as how we found the first one. So in the same fashion, you can add more features after you found one already using this scheme. So I can keep adding more and more slow features just as I would add more and more principal components. And the constraint here says that the features must be linearly decorrelated from each other. So not independent, just decorrelated. And that constraint is essential to ensure that the learned features capture the current slowest feature. And this complicating optimization problem, it's actually not too complicating, can be solved in closed form. I haven't worked it out. I'd like to when I have time someday, because I think SFA is a cool idea. But apparently it can be solved in closed form. But what's really cool that I want you to take away is the slowness principle, the idea of penalizing time. So SFA is a linear factor model, but it can be used to learn nonlinear features by applying a nonlinear basis expansion to X before running SFA. So just as we can do like polynomial regression and calculate polynomial features to feed into a linear model, and then we get some curve that best fits our line, we can also get a nonlinear feature extractor by feeding in nonlinear inputs by some nonlinear expansion of our data, or basis expansion or transformation. And I can also compose multiple SFA models, slow factor analysis models, and I can combine them to make deep nonlinear slow feature extractors. So I have all these stacked SFA models, and I can create this deep nonlinear slow feature extractor. And deep is better, right? Always. So here's an example. So we first learn a linear SFA extractor, apply a nonlinear basis expansion to the output, and then learn another linear SFA feature extractor of that expansion. So just keep doing that. Add more complexity. Okay, so 3 more slides on this, then I want to show you a picture. Actually, I'll show you the picture now. So this is a deep slow feature analysis extractor. Yeah, and you output the slowest features. Cool. Yeah.
So is the purpose of stacking SFA to uncover like slower features than like one SFA?
Yeah, I guess the goal is to disentangle more nonlinearity, add more nonlinearity to whatever you're extracting. Maybe the thing that you're extracting cannot be explained in linear fashion. Same reason we have deep networks, to add more nonlinearity, add more complexity and capacity to our model. So just as, I don't know if you seen this video, but some researchers found that the kernels that we use in CNNs, there's something going on biologically. So back in the 60s, I think, some researchers at Harvard recorded a cat's neuron activity as it watched edges fly across the screen, and it saw that edges caused the neurons to activate in a certain pattern that was akin to how CNN filters are learned once they're learned. And so that kind of tells us, or leads us to believe, that CNNs are biologically plausible as a way of visualizing the world. In that same fashion, SFA is also biologically plausible. And we like biologically plausible as AI researchers, right? When things are biologically plausible, people believe us more when we say things work with AI. Yeah, that's how we do it. That's how a robot should do it too. Yeah. So biologically plausible is always a good thing to have. So when trained on small patches of videos and natural scenes, SFA with quadratic basis expansion learns features that are similar to those of complex cells in the V1 cortex. When trained on videos of random motion in 3D computer-rendered environments, deep SFA learns features represented by neurons in rat brains that are used for navigation. So there's something interesting going on, which I really want to look into this more. I'm not an expert on SFA, but I think there's something interesting going on here. Here's a nice example with audio. I'm running short on time, so I'm not going to spend time on this, but feel free to look at this. It's on the slide deck on GitHub. Closing thoughts on SFA. Slowness principle is really cool, but it hasn't been the basis for any SOA application. It's unclear what has limited its performance. Perhaps the slowness prior might be too strong. Maybe we should instead impose another prior that says that features should be easy to predict from one time step to the next. Yeah, so object position is a useful feature regardless of its speed, but the slowness principle encourages the model to ignore positions of objects with high speeds. Cool. Sparse coding. Bruno Olshausen. Olshausen? How do you say his name? Olshausen. He's my hero. Olshausen and Field, 96, baby. Sparse coding is a linear factor model that is used for unsupervised feature learning and feature extraction. The word sparse coding refers to the process of inferring the value of h, and like most linear factor models, it uses a linear decoder plus noise to obtain a reconstruction of x. So in this case, remember I said that linear factors model differ based on the choice of prior they impose. In this case, sparse coding, we want to have a sharp peak near zero in our prior of h. Our latent variable prior is intended to have a sharp peak near zero for some reason. And so these two distributions satisfy that. The Laplace and the t distribution both have sharp peaks near zero. And so those are possible choices for the prior in sparse coding. It can't be trained with maximum likelihood. It is trained in an alternating minimization fashion where we encode the data and train the decoder to better reconstruct the data given the encoder. So if you know how GANs are trained, this maybe rings a bell about how GANs are trained. So unlike PCA, the encoder with sparse coding is non-parametric. That's exciting. And what the encoder does is it solves the optimization problem in which we seek the single most likely code value. And with our assumption of Gaussian noise and Laplacian prior, we're solving the optimization problem argmin equals lambda 1 norm of h. I think there should be 2 lines next to the beta. Or no, there shouldn't, that's right. Beta is another hyperparameter times the 2 norm squared of x minus wh. So anything important here? So I guess the beauty of non-parametric encoders is that it can theoretically minimize the combination of reconstruction error and the log prior better than any parametric encoder, in principle. Practice is a different game. And these are just some extensions that Andrew Ng and Goodfellow found. So Ng found that sparse coding features generalize better for object recognition tasks than features of a model based on a parametric encoder. And Goodfellow found that a variant of sparse coding generalizes better than other feature extractors when very few labels are available. Yeah.
Why can't we do like a Gaussian distribution?
For the prior on H? I don't know why they wanted a sharp peak near zero. The Gaussian's too flat near zero, unless you have like the SD of 0 essentially. They wanted the sharp peak probably to ensure sparsity in their codes that they find. They want to find like individual codes that are most important They don't want to just find like small amounts of everything. And so that's why I can imagine a peak near zero being important, to try and zero out most of the things.
So can that be applied to like other linear factor models, like the ones that assume the Gaussian distribution? If we just use the Laplacian distribution instead, that it would have like a similar.
You can certainly use whatever prior you want, but then the nice properties of whatever LFM you're using won't necessarily hold. And I don't have enough experience to say like what would happen if I used a Laplace prior when I'm trying to do something like ICA. I have no idea what would happen. That's just certainly a good research project question, of which your proposal is due next week. Forgot to say that. Here's an example. I have some images and I want to learn some latent factors about this image, and here's how we can do it. So I code this image into sparse features. And you can use it for image reconstruction. So from this, I have this image and I'm looking at a sparse component of it, some sparse components of it. So a lot of them are zeroed out, and the goal is to reconstruct the original image using the sparse components. And so my guess is that for this picture, the sparse coding algorithm are what picked these particular components as being the most important ones to reconstruct the original image. Sparse coding is saying that if I know those pixels, that's all I need to reconstruct the image. Those pixels are enough of a code of the original image. There's enough information in that sparse code of the original image. That's so many words, I'm sorry. There's some disadvantages. Let me read the most important one. It's not straightforward. It produces poor samples. So it's not. The takeaway from this slide is that it's not perfect, but it motivates the development of a deeper model that imposes a non-factorial distribution on the deepest layer code. So having a sparse code is useful, and I want to talk about why, but do that later. Manifold learning. This is cool. How many people know what a manifold is? How would you define a manifold?
Kind of, you have like a high-dimensional space, but within it you have some kind of like embedded surface that's like loaded, not as high-dimensional, essentially.
Yes. So a manifold is just like some space, but I want to learn a manifold that. So I have some data in this high dimension, and I want to learn this low-dimensional manifold that best captures the data. The geometry of the data, that is. So like when we do PCA, we're doing manifold learning. We're finding a smaller dimensional subspace that best captures the variance in our original data. That's what PCA is doing. PCA learns a manifold, but not very well. So linear factor models, including PCA and factor analysis, can be interpreted as learning a manifold. So when we talk about dimensionality reduction, we can also talk about manifold learning. We're learning a low-dimensional representation of our original data. And so that's what manifold learning is. And you can interpret PCA as manifold learning. And in particular, probabilistic PCA can be viewed as defining a thin pancake-shaped region of high probability. So a Gaussian distribution that is very narrow along some axes and wide along others. So PCA can be interpreted as aligning the pancake with a linear manifold in high-dimensional space. This interpretation applies to any linear autoencoder that learns matrices W and V with the goal of making the reconstruction of X lie as close to X as possible. That the encoder be H is this. So we can recover the latent factors by doing this change of variables. And the encoder computes a low-dimensional representation of H, and the decoder computes the reconstruction as follows. So we're just getting X back from H using the decoder. So we're learning an encoder and a decoder. That's what linear factor models do. They learn an encoder and a decoder. And in probabilistic PCA, the encoder and decoder that we learned minimize the reconstruction error. We want to find the best low-dimensional subspace that best captures our data. So we want to minimize the reconstruction error. Those are very similar statements. So those are the solutions: V equals W, mu equals B. Columns of W are an orthonormal basis that span the same subspace as the principal eigenvectors of the covariance matrix C. In PCA, the columns of W are the eigenvectors ordered by the magnitude of their eigenvalues. Yeah, and we already know that the eigenvalue corresponds to the variance of x in the direction of eigenvector Vi. Those are things that we knew already. So PCA is one manifold learning algorithm where we learn a low-dimensional subspace. There are a lot more. Here are some nonlinear ones. Well, I think isomap's linear. No, isomap's nonlinear. Locally linear embedding, spectral clustering, t-SNE. So those first three are very easy to do using sklearn. Sklearn has nice built-in functionality to do those first three nonlinear dimensionality techniques. So manifold learning methods, nonlinear PCA, diffusion maps, multidimensional scaling, MDS, and many more. There's other factor techniques that we didn't cover. So we covered a lot of different factor analysis techniques, but we didn't cover deep canonical factor analysis, multiple factor analysis, common factor analysis, image factoring, alpha factoring, factor regression models. There's too much to cover, right? And really, let me say next steps, and then I'll say my last spiel. So remember that LFMs are some of the simplest generative models and some of the simplest models that learn to represent data. And now, akin to how linear regression models extend to deep feed-forward networks, LFMs may be extended to autoencoders and deep probabilistic models that perform the same task but are much more powerful and flexible. So, as linear regression is to deep networks, LFMs are to deep probabilistic models. And let's see, I put this link here. Why did I put that link there? Oh, it's a demo. Dimensionality reduction. Yeah, you should look at this. I don't have time to go over it. Maybe I do, but where'd my slides go? Yeah, so look at this. Is a nice visualization that shows what manifold learning looks like. Going from a high-dimensional space to a low-dimensional space. Chris Kolaw's blog, he's probably like the best guy I've ever seen to make visualizations. Chris Kolaw is brilliant. Yeah, definitely the best visualizations out there for just about anything. So I definitely recommend checking out his post if you want to see more about manifold learning. Okay, so I apologized twice already. I'll apologize a third time. I'm sorry that my slides were very verbose. I'm sorry that I tried to cram too much stuff. And I'm sorry that I didn't give you any state-of-the-art models that you can use in your own work today. What I did want you to take away, what I hope to give you is a general understanding of probabilistic models, of latent variables, of why we want to find latent variables, or why we want to estimate them. And yeah, I really hope that you have a basic understanding of the relationship between latent variables and observed variables, and why we're interested in finding latent variables. One more thing that I'll say is that this stuff, while it's not SOA at all, many of the stuff that will be talked about in the subsequent weeks is SOA, state of the art, and it is based on this stuff. A lot of really cool stuff falls around the idea of basically estimating a distribution. And so, for example, generative adversarial network scans. All the cool stuff that they do is really fancy way to estimate the distribution of some image generation process. So many cool AI things can be thought of as just approximating a distribution. And so that's why it's really important to have an understanding of probabilistic models, latent variables, and the relationship. Are there any questions?
this is a little bit outside of the scope of our
That's okay.
session today. But do you think you could talk a little bit about the primary differences between autoencoders and variational autoencoders?
Next Tuesday will be all about that.
Okay.
Or next Wednesday, sorry. Can you hold off till then?
Yeah.
Okay. Yeah. Yeah. So next week we'll be extending this idea, and we'll be talking about autoencoders and different kinds of representation learning methods. So this lecture was kind of setting up the framework. Next lecture will teach you some cool models about how to estimate these things in the SOA manner. Except autoencoders aren't so SOA anymore, but maybe VAEs are okay. Sweet. Yeah. Sorry, I was super busy this week and didn't get a chance to make everything polished. But I hope you took away the main idea.